Okay. So guys, here's what we're up to today. We are going to start the next unit by actually taking our periodic tables and tearing them apart. Well, not tearing them apart, but getting an even clearer sense about how these things are all put together. So guys, this is going to feel very well, here, I'll show you. I'm going to leave no fuzziness about how to take notes today, even to the point, ready for this, where, all right, we already went over this, where I have drawn for you your notebook paper. Could this be any more clear? And what I'm going to do is I'm going to explain to you exactly how you want to lay out your notes today, so to be successful getting all of this stuff into your notes. So guys, here's what you're going to do. If this is your paper, notice I even made the line red. What you're going to do is this. First of all, you're going to, so you've already got it titled, right? Periodic trends. You're going to draw a and hold on, don't go yet, just watch. You are going to draw a skeletal version of the periodic table where you'll cut up the S and the P, don't cut up the D, and then what you're going to do is skip down 6 lines and then draw the F. And then, guys, this space down here becomes your note space. So these 6 lines right here and this space over here becomes hollowed ground. Don't mess around with that until I tell you to. And what you want, guys, is you'll notice that if this is the middle of the page, that's about where your S sublevel starts. So you want about, 3 at least inches over here, 6 lines here. So really this space should be as tall as this space is wide. So go for it. You're going to thank me later when we start filling up these spaces. So guys, as you're digging into this, let me sort of give you the overview for what we're doing. So what we're going to do today is we're going to first of all take the periodic table and we're going to break it up into all its parts. And we're going to give those parts names. Then, once you know the names on the periodic table, we are then going to talk about the trends that exist on the periodic table. And we're going to talk about 5 of them. As you move across and down the periodic table, how do these elements change? What about them is different? And you're going to find out that there are 5 trends that we're going to talk about. The first 2 will be relatively easy. The second one is going to become all important, or the third one is sort of all important and a little difficult. And then the 4th and 5th ones depend upon the 3rd one. Then when we're done with that, we're going to talk about this heavy blue stair-stepped line that sort of wiggles its way down the right-hand side of the periodic table. And then we're done for the day. Then guys, when I see you on Monday, we're going to do a lab. And we'll actually not be going into lab for lab. We'll be in here. And it's a fun one. If it were after Thanksgiving, we could play Christmas music while we do it. But it's not, so we can't. It's a rule. It's true. Santa this year finally put down his foot and said, you play Christmas music before Thanksgiving. Game over. You don't mess around with Santa. Although my wife made me go with coals with her last night. Good heavens. Full on Christmas. Not good. You guys all caught up? You ready to go? Got it laid out? Not yet? Is it pretty bad? You are a lefty, though. You have an excuse. I love that some of you are using little things as straight edges. That makes me happy. There you go. You guys done? Good heavens, you're like a hoity-toitles. Oh. You guys know any jokes? No? You heard about the dog that hobbled into the bar, Said I'm looking for the man that shot my pa. Come on, that's not bad. That's all I got. So you got to be done because I'm out of jokes. You guys done? Yeah. All right. So guys, it's important that you understand this. Do not mess around with this space, because what we're going to do is we're going to start by taking some notes. There are some terms that you need to know, and those are going to go down below the F sublevel. Do not write in this space until you see me writing in this space, okay? All right. So now, guys, here's what's going to happen. We are going to zoom in to this part of the periodic table. Now, what you're going to see is my notes are going to show up here, which is going to make you think that that's where your notes should go. But you're not going to do that, right? Because you understand that your notes go down below the F, right? All right, so here we go. So guys, first two terms that you need to know relative to the periodic table are period and group. And they go like this. A period on the periodic table is a horizontal row on the periodic table. Now, because you learned so much in the last unit, you know that there are 7 periods on the periodic table. You numbered them, and what do those 7 periods represent? The energy levels, right? Energy levels 1 through 7, broken into sublevels S, P, D, and F. But guys, you understand that the periods, the horizontal rows, are the energy levels, and there are 7. You good? Okay, now guys, groups. Groups are the vertical columns. Now let's try this one on for size. Because you know that the groups, these vertical columns, you learned something as you were drawing Lewis dot structures, right? What did you learn about all of the elements in the first group? How many dots do they have? 1. And the second group has 2 and 3 and 4 and 5 and 6 and 7 and 8. So what does that tell you about the groups? Well, it tells you guys that elements in the same group have the same number of valence electrons. That means they react the same. They have the same number of Lewis dots, the same number of valence electrons. Therefore, they react the same. Y'all good? All right. So now, guys, what we're going to do is I'm going to get rid of these. Can they go away? All right. So what we're going to do is we're now going to start labeling the periodic table. And guys, the first thing that we're going to do is we are actually going to number the groups 1 through 8. So go ahead and do that. You'll notice that we did not number the D or the F sublevel. Why not? Because they're not valence. So guys, what do these numbers tell us about the elements that are in these groups? Notice I used the term properly. What do the numbers tell us about the elements in those groups? The number of dots, the number of valence electrons. So guys, we are no longer going to just sort of call this the S. We're no longer going to call this the P. We're going to talk about groups 1 and 2, and we're going to talk about groups 3 through 8. You good? Okay, now, each one of these groups, guys, it turns out actually has a name. In addition to a number, they have a name. Now, guys, you already know the name for group 8. What are those? The noble gases. We'll get there in a minute. But, guys, they all have names. You only need to know groups 1, 2, 7, and 8. So these are the names. Group 1 are what are called the alkali metals. I'll zoom into this so you can see it a little better. These are what are called the alkali metals. They are, in fact, all metals, and we call them the alkali metals. So some of you right now are wondering, wait, is hydrogen an alkali metal? And the answer is yes. Hydrogen is a metal. It's a gas, but it's also a metal. Hydrogen is, in fact, a gaseous metal. Okay, so there's group 1. Guys, group number 2 is similar to 1. These are what are called the alkaline earth metals. And guys, I couldn't get the word metal to fit and make alkaline earth big enough that you could read it. So in yours, you want to include the word metal because these are metals as well. And these are what are called the alkaline earth metals. How you doing? Oh, yep. No, in this case it's not. Helium is not a metal. Yeah, that's, Josh, that's a great question. No. So helium in this thinking goes back to the right. You guys good? Okay, so zooming out. Now, we're going to move into the middle. And guys, I told you you only need to know the names of groups 1, 2, 7, and 8. But guys, the D sublevel is not a group. It's a big old collection of groups. There's 10 of them, as you know. But this entire region, the D sublevel in the periodic table, has a name. These are what are called the transition metals. So all of the metals in the D sublevel are the transition metals. Why transition? Because we are transitioning from the valence S to the valence P. So they're sort of the bridge between the two. Then guys, moving over to 7 and 8. 7 may sound familiar. These are called the halogens. Typically people have heard of those because of halogen headlights that they're putting in vehicles. They're the bright, shiny white ones. And then guys, you may as well just do noble gases because you already know the noble gases. Okay. So we've got the names for groups 1 and 2, the transition metals 7 and 8. Now guys, the last thing that you need to know the name of is the D and F sublevel. So let's talk about this really quickly and then we're going to start talking trends. So here's the way this goes. You ready? This is actually pretty good logic. So guys, down here we have the F sublevel. You know that this is the 4F. Now where does this technically belong? It belongs up here, right? It belongs right after lanthanum. It goes 55, 56, 57, 58. So it goes right after lanthanum. And because of that, they named these the lanthanoids. Kind of sounds like a horrible disease, but it's actually relating it back to the periodic table so that you know that these dudes are anchored to lanthanum. Now guys, if you understand that logic, you should be able to name the 5F. Because if the 5F or the 4F comes after lanthanum, what would the name of the 5F be if it comes after actinium? The actinoids, not actiniumoids, but the actinoids. There you go. So guys, those are all of the parts of the periodic table that you need to know. Eventually you'll be held accountable for them. But guys, the bottom line is this. As we move forward in this class, we are no longer going to call this the D sublevel. These are the transition metals. These are well, we've never really had a name for them, but we're going to talk about the alkali metals, and you're going to need to know they're these. So these are going to be the names that we're going to give these elements moving forward. You good? All right, now watch what's going to happen. The F sublevel is going to go away, and we are going to zoom out, so this is going to get smaller. Now we're going to start treading in the hallowed ground. You ready? Here's what's going to happen. Guys, eventually these spaces are going to be filled up with 5 arrows. So you're going to have 5 arrows going down here and 5 arrows going to the right here. And each one of those arrows is going to have a label, and each one of those arrows is going to have words written on them describing the trends. So as you do this, you need to picture you need room for 5 arrows, and you need room for 5 arrows. That's why we skipped 6 spaces. And then guys, as we go through these, we're going to get into sort of a pattern. So it goes like this, but please don't write anything down. So the first trend that we are going to talk about is for atomic number. But guys, this does not go in the hallowed ground. Where does atomic number go? Down in your note space, right? Down below, what was the last thing you wrote? Group? Group, okay. But here's the deal. You guys know what atomic number is, right? So I don't think you need to, it's up to you. If you need to remind yourself that atomic number is the number of protons in the nucleus of an atom, feel free to write that down. But if you do, write it down beneath where you wrote down the stuff you wrote down about groups. Do not write this down in the hallowed ground. So what we're going to do is we're going to talk about the trend on the periodic table for atomic number. We remember that that is the number of protons in the nucleus. So here's what we're going to do. Check it out. Go ahead and do this. We are now going to draw in an arrow pointing down and an arrow pointing to the right. And again, guys, eventually they're going to be 5, so use your space judiciously. But we've got an arrow down and an arrow right. Now what we're going to do is we're going to label the arrow. And of course, you all remember the abbreviation for atomic number, Z. So we're going to put a Z above it and a Z to the left of it. All right. So now, guys, we're ready to start talking about trends. You ready? Grab your periodic tables. And guys, today is reckoning day. If you ain't got one of these periodic tables, the periodic table that you do have is about to fail you. This is the day that explains why I've been demanding you buy these. There's data on here that you need that aren't on other periodic table. So here we go, guys. We are now going to talk about this, the trend as we go down a group for the atomic number. So guys, remember the atomic number is the big blue number in the upper left-hand box. And just allow your eye to scan down all these groups. Go ahead and do it. And as you're looking down the groups, do the atomic numbers get bigger or smaller? Bigger, right? If you go down the alkali metals, it goes 1, 3, 11, 19, and so on. If you go down the alkaline earth metals, it goes 4, 12, and 20. If you go down the halogens, it goes 9, 17, 35. Without exception, every time you move down, the atomic number gets bigger, meaning there are more protons in the nucleus. You guys sold on that? Okay, so let's label it. What that means is these numbers go from smaller to larger as you go down a group. That is the trend. And again, guys, you understand that that trend tells us that as we move down, there are more protons in the nucleus. So now let's do the same thing, only let's go left to right across a period. And guys, notice I'm using all these terms correctly. Down groups, across periods. So as we go across a period, what happens to the atomic number? Does it get bigger or smaller? Bigger, right? Without exception, you go across the first period and it goes 1 and then 2, the next period 3, 4, 5, 6, 7, 8, 9, 10. There's no exceptions to the rule. The atomic number always goes from smaller to larger every time without exception. So, I know that was relatively simple. This is going to get harder in a minute, but you now understand the trends for atomic number. They get bigger as you go down, and they get bigger as you go to the right. You love it? Okay, now let's do this. What is the overall trend on the periodic table? Where, given these trends, where would you expect to find the biggest atomic numbers? Bottom right, right? The big ones are down, the big ones are right. The biggest atomic number should be bottom right. Is that the case? Yeah. What about the smallest atomic numbers? Top left, and sure enough, there's hydrogen. That's the smallest, and the trend holds true. You get it? All right. So now, guys, let's try this. Atomic mass. Again, don't write it in the hollow ground. Write it down beneath if you need, but most of you remember the atomic mass is the number of protons and neutrons in the nucleus of an atom. If you want the reminder, feel free to write it down. And now, guys, we're going to fly in, not surprisingly, you're starting to figure out the pattern. We're going to fly in 2 arrows. I have the advantage of doing this digitally, so the arrow that we're currently focusing on is blue while everything else is black. And now, guys, what are we going to do next now that we've drawn our arrows? Label the arrows. What's the abbreviation for atomic mass? A. So we're going to label both of those A. Now that we've got this all labeled, we need to again look at the trends. So let's talk down a group first. You remember that the atomic numbers or the atomic masses are the small numbers in red. And as you allow your eye to scan down a group, what's the trend? Light to heavy or heavy to light? Light to heavy. Yeah. As we go down a group, without exception, these things go from lighter to heavier. Now, I know you know what's coming, so let's do it. As we go left to right, what is now the trend in atomic number? Did they go light to heavy or heavy to light? Light to heavy, right? The light ones are on the left, the heavy ones are on the right. Anyone have any problems with that? I do. What about this? Look in the transition metals start at like maybe iron, number 26. So iron has a mass of about 55.8. Not surprisingly, cobalt is 58.9. It's heavier. Now go to nickel, 58.7. Nickel is lighter than cobalt, and yet nickel is to the right. We just found an exception to the trend. First of all, can we explain it? What would explain the fact that nickel is lighter than cobalt when it should be heavier? We know that nickel has one more proton than cobalt because it's 28. What would make it lighter? Not less dense. Think about what the atomic mass tells you. Protons and neutrons. Good, Caitlin. It has less neutrons. Remember, guys, these are averages, right? And so what that tells you is that even though nickel does have one more proton than cobalt, it must, on average, have fewer neutrons, making the average mass lighter, even though it's got one more proton. Get the idea? Okay, but here's the important point. Does it invalidate the trend? Is the trend still lighter to heavier? Absolutely. So guys, it's an important thing you've got to understand. Trends are trends. They are the things that tend to be true. And if you find small deviations from the trend, it doesn't mean the trend is broken. It just means there are some exceptions to the trend. And if we can explain them, they don't invalidate the trend. That's important. You get the idea? All right. Guys, this is about to get hard. Let's make sure we're clear on one more thing, and then let's do some hard stuff. Where are the big porkers on the periodic table? Bottom right. These are the heavy guys. These are the sumo wrestlers of the periodic table. Guys, where are the little light guys? Top left. You good? All right. Now let's make this more difficult. We are now going to get into things that we've never talked about before in this class. I know that you're going to need to write these things down before we start talking about their trends. The next one, guys, is atomic radius. You definitely want to write this down. This one's hard. I'll just be honest with you. This one is very conceptually challenging. The second part of it, you're going to understand the groups. The trend in the groups. But guys, the trend in periods can be tricky. So let's talk. Guys, first of all, you all know geometrically what a radius is, right? If you've got a circle, what's the radius? The middle to the perimeter, right? To the outside. But if our circle is an atom, what's in the middle? The nucleus. And what's on the outside? Valence electrons, not just the electrons, it's the valence electrons. So guys, this is the distance between the nucleus and the valence electron shell. So what are we going to do next? Now that we've got, well, I'll wait. I don't want to rush you. So now that we've got it identified, we understand what the atomic radius is. Next, we are going to draw our arrows. So draw in an arrow from the left, on the left, pointing down. Draw in the arrow, of course, pointing right. And then, guys, what we're going to do is this. We are going to abbreviate it. This is not an accepted abbreviation. We're just going to abbreviate it AR for atomic radius. You guys good? Now we're going to do something different. We are now, in your notes section, going to talk about the explanation for the trends that we are about to find. So guys, down a group, we are going to talk about why the trend that we see is true. But the first thing we've got to do is identify the trend. You ready? Grab your periodic tables and flip them over. If you don't have one of these periodic tables, you don't have a flip them over. Now, guys, go down to the double top secret decoder key down in the bottom left-hand corner. And you will notice down there on the left-hand side of the decoder key that it says covalent radius and, well, it says symbol, but then it says covalent radius in angstroms, that A with the halo, which is 10 to the negative 10th meters. Amazingly, you learned that back in August. And then atomic radius, which is also in angstroms. Notice that the radii, those two numbers are both in that little pink box. Now, we are not looking at covalent radii, we are looking at atomic radii. So now you know where it is. It's the bottom number in the pink box. Now go to the periodic table and start looking down the groups. So what happens to the atomic radii? Looking at the alkali metals, rounding, 0.8, 2.6, wait, 2.6? No, sorry, 2.1, 2.2, 2.8, 3, 3.3, and so on. They appear to be getting bigger. So now let's go and look through some other periods, or groups. You pick. Whatever group you go to, what is happening to the radii of these elements? They're getting bigger. Do you see any examples where they're getting smaller? That's good, because there aren't. So guys, the trend is this. As we go down a group, they go from smaller to larger. But guys, before you write it down, let's talk about why. Because you know why. Why do they get bigger as we go down a group? What is happening to these atoms as we go down? So these are in the first energy level. These are in the second and the third and the fourth, fifth, sixth, and seventh. And guys, as we go down the groups, we are moving out energy levels, right? We're adding more layers to the onion, and that makes the atoms bigger. So we're going to say it like this. As we go down a group, these increase because we are adding additional energy levels. Now guys, for some of you this may be fuzzy, so I want to show you what we're talking about. Don't try to write down what you're about to see. Can I show you? So guys, it goes like this. You ready? Looking at group number 1, the alkali metals, these guys. So guys, first of all, hydrogen. Hydrogen looks like this, right? Using the Bohr model because it works here. 1 proton, I'm not even doing neutrons. 1 proton, and did I do neutrons and any of the rest? No. So 1 proton, 1 electron. Now when we move down to lithium, what's that going to look like? It's going to look like this. 2 electrons in the 1s, and then 1 electron in the 2s, but the 2s, that larger cloud, is bigger than the 1s, and therefore it's bigger, right? So what then is sodium going to look like? Well, it's going to now have a 3s. So we've got these 2 electrons in the 1s, these 8 electrons in the 2s and the 2p, and then this 1 electron in the 3s. We're adding layers to the onion and the atom gets bigger. Is that good? Notice what they all have in common though. What's that dude right there? The 1 valence electron. That's why all of these have 1 dot, right? Tying it back to what we did before. This is the 1 valence electron that would show up in the Lewis dot diagram of any of the elements that are in group 1. The thought being, though, that valence electron as we go down is further away because it's in a bigger s sublevel. Are you good with the concept? Please ask questions if you need. You're good? Okay. So guys, I would propose we're ready to do this. Smaller to larger. And again, why does it go smaller to larger? We're adding layers to the onion. Okay, you ready, guys? This is about to get hard. You ready? This is tricky. Here we go. Change this down here, atomic radius across a period. So down below where you said down a group, add across a period. So guys, as we go across a period, grab your periodic tables. Take a look at what's happening. Compare the numbers. They're getting smaller. Whoa. And understand, guys, there are exceptions, but let's just do the second period, for example. 2.1, 1.4, 1.2, 0.9, 0.8, 0.7, 0.6, and 0.5, rounding. They're getting smaller. And guys, that is universally the case, with a few exceptions. But that is universally the case across the periodic table. As you move from left to right, surprisingly, these elements do not get bigger, they physically get smaller, more compact. Thoughts on why? What is changing? And guys, I've already given you the answer. It's in one of the other trends that we did previously. What is changing about the atoms as we go from left to right that would explain the fact that they're getting smaller, counterintuitively? It's not heavier. Although you're right, they do become more dense because they get heavier and smaller, which increases their density. But what would make them get smaller? Guys, what holds an atom together in the first place? The attraction between the nucleus and the electrons, right? So what is happening to the nucleus as we move from left to right? What are we adding for sure? Protons. And what does that do to the charge of the nucleus? Makes it more positive. And as the nucleus becomes more positive, what does it do to those negative electrons? Sucks them in closer. Do you get it? So guys, the idea is this. As we go across a period on the periodic table, we are adding protons to the nucleus. That makes the nucleus stronger, more positive. And that stronger, more positive nucleus pulls all those electrons tighter together, and the atoms get smaller. So let's summarize it this way. As we move across a period, the radius decreases due to an increased nuclear charge. And you know what? I want to add this. As protons are added. So guys, as we go across a period, surprisingly, these things become smaller. And they become smaller because the nucleus is getting stronger and it pulls everything tighter together. Is that okay? Let me let you fit, because I want to show you this a couple different ways. So you okay? Can I show you? Okay, so do this, guys, watch. So we're good on this, right? Why are these getting bigger as we go down group 1? We're adding layers to the onion, right? Now, guys, let's look at groups 2 and 3. So we're now going to look at this group and this group. So we're really thinking now that helium is a neighbor of hydrogen again for this purpose. So, guys, when we go over to helium, this gets smaller. Why does it get smaller? Well, helium's got 2 protons. Yeah, it has 2 electrons as well, but this stronger nucleus pulls everything tighter together. Now let's do this again in group 2, or in period 2. So now, guys, we go from lithium with 3 protons to beryllium with 4 protons. And 4-proton beryllium pulls everything tighter together, and it's smaller. Then as we continue on to boron, that will have 5 protons, an even stronger nucleus, and it is even smaller. And guys, that trend continues. As we go down to sodium, we understand that it's bigger because we're into a new, bigger level. But then as we go to magnesium with 12 protons, that is smaller. When we go to aluminum with 13 protons, that is even smaller. And the trend just continues across the periodic table. Do you get it? Yeah. No, because remember, like, what do you mean figure out? No, because remember, when we're trying to go after element 114, that's a nucleus issue. It's not an electron issue. And actually, interestingly, Josh, one of the things that they didn't mention is when they put these nuclei together, the first thing they do is they strip all the electrons off. So when they say that they're colliding sodium, what was it when they made that? What, calcium and plutonium, they actually strip the electrons off first. They just need the nuclei without their electrons. Yeah, yeah. Yeah. That violate the trend. And honestly, Landon, I would love to sit down and talk with you about that individually. Frankly, it's the first thing that we do in AP chemistry. The very first day in AP, we talk about why those... Actually, what I do the first day in chemistry is I give my students laptops, and we actually graph atomic number versus radius, and you can actually see that there's a spike-like trend, but there are little hiccups in it, including the one that you pointed out, and their first writing assignment is to talk about why it's there. And I'll tell you quickly, the answer is because they're in the D sublevel, right? The transition metals. Yeah, the reason is because the transition metals actually get so close to that S sublevel that they start to push on it a little bit. But it's beyond what you need to know. So, yeah. You guys okay with the trend? So, guys, this I made up last year. This to me really helps. You ready? Periodic table. As we move left to right, what's going to happen? They get smaller. So when we do this, from hydrogen to helium, it gets smaller. Now when we jump from hydrogen to lithium, what's going to happen? When we make this jump, what will happen? From here to here, it'll get bigger, and then as we move across the period, it will get smaller. So it goes initially bigger and then smaller. And then when we jump down to sodium, it again will get initially bigger and then smaller. And then what about when we jump down to potassium? Initially bigger and then smaller. So as we go down groups, you can see that they're bigger. This gets bigger and bigger and bigger, and this gets bigger and bigger and bigger. So as we go down groups, they get bigger, but in the periods, they're getting smaller because of the stronger nucleus. You get the idea? So let's go back and put this on our periodic table. So guys, atomic radius then, surprisingly, goes larger to smaller. Okay. Now, guys, let's see if you really understand that. We've got 2 more trends to go. And both of the trends that we are now going to talk about all hinge on atomic radius. So let's do this really quickly. You ready? Where are the smallest elements on the periodic table? By size, where are they? They are top right. These dudes. These are the smallest elements on the periodic table. Not necessarily the lightest, but they're the smallest. Now, where are the big elements on the periodic table? Bottom left, okay? You okay with the trends? Okay. Now, guys, the next one that we need to talk about is electronegativity. If you were to walk up to anybody that's ever taken or is now taking AP chemistry, and if you said to them, what is the most important thing you learned in general chemistry to get ready for AP chemistry, they would tell you this. Guys, electronegativity is one of those concepts that informs so much of what you will ever do in chemistry. This one's important. So why is it so important? Well, let's define it. Guys, electronegativity is defined as an atom's ability to steal electrons from other atoms. Now, why is that important? Because that's how they bond. When atoms bond together to form compounds, what they're trying to do is steal each other's electrons. So guys, electronegativity is really a measure of reactivity. So it's important to understand because it tells you not only how elements bond together, but also the types of compounds that they make when they bond. Okay, so electronegativity is an atom's ability to steal electrons from other atoms, or you can just think of it as stealing power. You don't need to know the formal definition. If you just want to think about stealing power, you are money. Now, guys, there's a term that I need to share with you which means absolutely nothing to you now until I show you my super high-tech electronegativity animation of science, which I'm about to do. It'll be life-changing. You ready? Here's the term. Electronegativity depends on a thing called shielding. So what is shielding? Shielding is the interference that is caused by electrons that surround the nucleus. Let me make this up. There we go. So guys, shielding is the interference that is caused by electrons that surround the nucleus. I know that means nothing to you, but I'm about to show it to you. We're even going to turn out the lights for this. It is that beautiful. You're going to love it, man. Are you ready? Just sit back and experience the magic. Hurry. Are you done? Done? Can this go away? No, okay. You can tell I'm all excited to show you my little creation and you're making me wait. You ready? All right, here we go. So, what on earth does it mean to steal electrons? And how does shielding play a part in this? I'm glad you asked. Let me show you. Here we go. Well, I forgot to draw in the arrows. Crap, draw in the arrows. I was all excited. And then let's label them EN for electronegativity. See, I'm even making myself wait. It's a hard life. You got it? EN for electronegativity? All right, now I get to show you. Here we go. What could this be? An electron. So what we're going to do is we're going to try to steal this electron. And we're going to figure out who are the better stealers. It's kind of like a tug of war. Now, in order to figure out who are the better stealers, let's get some atoms that we understand some things about. I would suggest that hydrogen's fairly familiar to us. It's up here. 1 proton, 1 electron, hydrogen atom, right? Now, let's grab another alkali metal to sort of play this who's the better stealer game, and let's get really wild and crazy, and let's grab potassium. Okay, now here's the question. Which one of these atoms is more electronegative? Which one of these atoms is a better stealer? Well, in order to figure that out, let's talk about how stealing works. So guys, what's the charge of this electron? Negative. What's the charge of all of these electrons? Negative. What's the charge of the nucleus? Positive. So, if hydrogen is going to be able to grab a hold of this electron and steal it, which part of this atom is going to be attracting this electron? The electron or the proton? Proton, right? So you ready? This proton reaches out to the electron and tries to pull it back. Okay. Now, here's the thing though. That's not the end of the story, because all the while this proton is pulling that electron in, what is this electron doing? Going, you ain't coming over here. And what do we call that? Shielding. Get it? This is the repulsion of the electrons around the nucleus. Now, let's take a look at potassium. Guys, 19 stinking protons. What do you know about the strength of this nucleus? It's like reaching out to pull that electron back. Guys, that is a really stinking strong nucleus. But what about all these electrons? What are all 19 of those electrons doing? They're going, you ain't coming over here. So guys, here's the question. Who wins? Which will be a better stealer? A weak nucleus, which by definition doesn't have a lot of shielding, or a stronger nucleus that also by definition has a lot more shielding? Which is the better stealer? You ready? This electron's going to go in that direction. Wait for it, because hydrogen's the winner. It even sparkles. Yeah. Now guys, we understand now why. Hydrogen has a weaker nucleus, but it has less shielding. Don't miss this, guys. Weaker nucleus, but less shielding, and that allows hydrogen to be a better electron stealer. But guys, this trend is universal, and we sum it up like this. Smaller atoms are stronger atoms. It is exactly the opposite of the way you think the world would work. You look at our world and you can clearly see that somebody like Paxton is stronger than somebody like Caitlin, because Paxton's so much bigger than Caitlin. Although it may not be true. She's kind of wiry. But guys, the point here is that in our world, things that are big tend to be strong. In the subatomic world, it's exactly the opposite. Small things are stronger. Wait. Small things are stronger. So how do we know which ones are the strong things? They're always going to be the small things. So wouldn't it be nice if you knew the size of these things? Because if you knew the size, you would know the strength. Oh my gosh, you already know the size of them, because what did we just do? The atomic radius. You get it? Guys, that's why we did atomic radius. Because if you know the ones that are small, you know the ones that are strong. So can't you go ahead and write the trends in on your lines for electronegativity? If the ones at the top are small, they're going to be strong. And if the ones at the bottom are big, they're going to be weak. And then similarly here, if the ones on the left are big, they're going to be weak. And the ones over here that are small are going to be strong. So guys, here's the question. Who is the super butt kicker on the periodic table? Where would we expect to find it? Top or bottom? Top, left or right? Right. So who should it be? Helium. Why ain't it helium? Because helium's a noble gas and it's all full up. So the super butt kicker is going to be the one that's not only top right and therefore small and strong, but also has some space to put its stolen electrons. And who's that going to be? Fluorine. Now guys, do this with me. Grab your periodic tables again on the back and look down at the decoder key. Now if you look at the decoder key on the right hand side, you'll notice that it says electronegativity. This is on your periodic table. And if you go and look at the electronegativity of fluorine, what do you notice that it is? 3.98. That means nothing to you. And it doesn't have units. Electronegativity is a dimensionless number, and it's only used for comparison. But guys, the electronegativity of fluorine is 3.98, and that's huge. And while we're at it, why don't you go look at the electronegativity of helium? It's not 0. What is it? It's a dash. It means it ain't got one. So guys, if we understand now that fluorine's the butt kicker, just a second, Mason, who's ready for this? Who's the big fat sissy? Because it is the fat ones that are the sissies. Who's the big sissy on the periodic table? Bottom left, francium. Guys, francium gets his butt kicked by everybody. The only hope that francium has is that he's actually so radioactive that many times he goes away before he gets his butt kicked. But guys, francium's a big sissy. Go ahead, Lex. Was that your question, Mason? Yeah. So do you understand the fluorine-francium thing? Okay, now let's look. Guys, xenon. If you allow your eye to scan down the noble gases, you'll notice that as you'd think, helium, neon, and argon and krypton do not have electronegativities, but xenon does. What does that mean? It means that xenon can steal electrons. And now you're going, wait, how's that happen? Well, guys, the first thing you need to know is it doesn't happen naturally. We can force xenon to take electrons. Where does it put them? Come take AP next year. But guys, you can actually force, I'll just tell you really, it puts it in a D sublevel. Okay, but guys, you can force xenon to take in electrons even though it doesn't want to. Again, understand it doesn't happen naturally. We have to force it to happen, but that's the explanation. Mason, was that your question as well? Okay, you guys good on electronegativity? All right, one more to go. So guys, here's the deal. See right here? On this side of the quarter, this is electronegativity. Now we're going to look on the other side of the quarter. We're going to look at the other side of electronegativity. If electronegativity is stealing power, then the thing on the other side is going to be keeping power. And that's called ionization energy. Guys, ionization energy is the amount of energy needed to remove an electron from an atom. So again, ionization energy is the amount of energy needed to remove an electron from an atom. Why do we call that ionization energy? Because when you move an electron from an atom, guess what it makes? An ion. A positive ion, but it's an ion. So guys, we call this ionization energy because it's the amount of energy needed to take an electron from an atom. So we can think of this as keeping power. The higher the ionization energy, the harder it is to steal electrons from atoms. Now guys, here's the way this comes together. It still follows the smaller is stronger trend. Because the same thing that makes an atom a good stealer makes it a good keeper. Not only are greedy people good at taking money from people, it's really hard to get money away from greedy people, right? Yeah, everything I ever needed to know I learned in preschool. Guys, if you ever walk into the preschool at your church and watch the kids, there's going to be one kid that has stolen all the toys from everybody else. And try taking one of those toys away from one of those kids, you got World War III on your hands. Guys, it's the same thing. Atoms that are good at stealing are also good at keeping. As a result, when we draw in these arrows and label them IE for ionization energy, the trends that hold for electronegativity are the same as the trends that hold for ionization energy. The strong ones are at the top, the weak ones are at the bottom, the weak ones are on the left, and the strong ones are on the right. So not only is fluorine really good at stealing electrons, it's really hard to get electrons away from fluorine. The trends are the same. And guys, we're not going to look at them now, but ionization energy numbers are also on your periodic tables. If you want to look later, you'll see that the trends persist. How'd we do? 5 trends. Guys, can we wrap up in the next 3 minutes and call it a day? Okay, here we go. You are now done with this. I think a lot of you have probably switched onto the back of your periodic table or the back of your notes page. Guys, we got one more thing to do, and it's this: metals and nonmetals. And it goes like this. You ready? I know that you guys have been laying awake at night in your beds, just pondering, what could it be? As you look at your periodic table and you see this heavy blue line that stair-steps its way through the periodic table. So let's put those restless nights behind us and let's talk about what that heavy blue line is. Guys, this heavy blue line separates the metals from the nonmetals. And as you know, these are the alkali metals, and these are the alkaline earth metals, and these are the transition metals. So all of the elements on the left-hand side of this line are metals, including the actinoids and lanthanoids. So everything over here is a metal. That's a lot of them. What are these? Those are the non-metals, including the noble gases. But then, guys, what about these dudes that sit on the line? They are what are called the metalloids. So you may want to write that. Do I have that in my notes? I don't think I do. I should include that. Let's just do that right now. That would be a good thing to add. So guys, those are what are called the metalloids. And these are the ones that are above and below the staircase. Now guys, understand that when we say above and below, we don't mean diagonal. So for example, carbon is not a metalloid. It's above or below. So boron, aluminum, silicon, germanium, arsenic, antimony, beryllium, and polonium. For those of you that are interested in computers, some of those elements may have sounded familiar because we make computer chips out of them. Because we call computer chips semiconductors. Metals conduct, non-metals don't. But the metalloids are semiconductors. That's why we make computer chips out of them. Okay, so with that said, let's talk about the metals, shall we? Guess what? You already know all the answers. So guys, the metals are over here. So how many valence electrons do they have? A lot, or just if one or two, right? They ain't got very many. The metals do not have a lot of valence electrons. Now, what about this? Given the trends on the periodic table, are the metals big or small? What happens as we go left to right? Do they get bigger or smaller? Smaller, because the nucleus gets stronger. As we go left to right, they get smaller, right? So what are the metals if they're on the left? They're big. So if they're big, are they weak or strong? Weak. So guys, the metals are big and fat and weak. And as a result, they lose electrons. Metals are electron losers. And if metals, because metals lose electrons, will they be positive or negative? Positive, and what do we call positive ions? Cations. Okay, so guys, in addition to that, there are some things you need to know about metals. First of all, they conduct and electricity. If you don't believe me, touch a hot pan or a power cord. They conduct both. Why do they conduct both? Because they're electron losers. Those electrons that they can lose so readily actually make them good and conduct both heat and electricity. In addition, they tend to be solids, with the exception hydrogen. Hydrogen is a gaseous metal. And their solids tend to be hard which means hard, shiny, which means shiny, ductile, which means you can stretch it out like taffy, and malleable, which means smushable. If you hit a metal with a hammer, it dents or flattens. It doesn't shatter. So malleable is the opposite of brittle. So their solids tend to be hard and shiny and ductile and malleable, and that's all because, well, we'll find out later, it's all because of their electrons. All right, so you ready? Nonmetals, and we're done. Same checklist. How many valence electrons do the metals have? A few? Nonmetals, over here, they have a bunch. They got many. So what about their sizes, big or small? They're on the right, so they are small. So are they strong or weak? Strong, they're the butt kickers. So these are small and strong. As a result, will they lose electrons or gain electrons? Gain electrons, and when you gain electrons, what does your charge become? Negative, and what do we call negative ions? Anions. And guys, you also need to know that these things insulate, they don't conduct. They don't conduct heat, they don't conduct electricity. And they can be solids, liquids, or gases. They have a lot of freedom in terms of the state that they're in. So gang, we be done. You already have your homework, and let me tell you right now, guys, there are some questions on your homework that we did not directly cover in class. They're going to require that you think and apply the things you learn. I know, heaven forbid, but you're going to have to think about the things that you learned and apply them in unique settings. So we will grade the homework on Monday. We will do a lab on Monday, which I really think you're going to like. And I'm seeing that the bottom of this. Oh, you know what, guys? There's actually one more thing here that got cut off. Sorry. Let me just throw this to you really quick. Guys, in addition to this, the solids, the non-metallic solids tend to be brittle. Let's just put brittle. That'll work. So guys, again, as you're sitting down to do this homework, you've got some time right now, and I'll throw the answers on the wall. But guys, be ready for these questions to be a little challenging at times. Not that you can't do them, you're just going to have to think.